Hi, so this is problem 4.2, and in this problem we are applying the conservation of mass. The problem is at page 211. In this problem we are given that we have a liquid propane enters an initially empty cylindrical storage tank at a mass flow rate of 10 kilogram per second. Flows continues until the tank is filled with propane at 20 degrees Celsius, 9 bar. The tank is 25 meter long and has a 4 meter diameter. Determine the time in minutes to fill the tank. So first thing what we want to do is we want to write down what is given and what we need to find. So in this problem, the fluid that we are dealing with is called liquid propane, or for short LB. So this is a liquefied form of propane gas. It is commonly used as a fuel for heating, cooking, and industrial applications. And this liquid propane is stored under pressure to maintain its liquid state and turns into gas when released. And remember, this liquid propane that is under pressure enters initially an empty cylindrical storage tank. This tank, the length of the tank is 25 meter and the diameter of the tank is 4 meter. When this liquid propane tank enters the empty cylindrical storage tank, it enters it with a mass flow rate of, at the inlet, 10 kilogram per second. When the tank is filled, the tank have the temperature of 20 degrees Celsius and a pressure of 9 bar. The question is how much time it takes to fill the tank given the mass flow rate and the characteristics of the liquid propane inside the tank with temperature 20 degrees Celsius and pressure of 9 bars. So first thing, let's draw a schematic. So let's take a look at this propane gas tank. Now, initially, it is empty cylindrical tank. Next, let's draw this line, and let's say this line represents the fill level. The liquid propane tank enters at the inlet of the tank to fill the tank all the way on to the top with a mass flow rate of 10 kilogram per second. When the tank is being filled, the tank propane temperature is 20 degrees Celsius and a pressure of 9 bar. Now this is something that you can do on the side. One, identify your system by drawing the system boundary and write down what is the system type. And obviously this is a control volume. So the first thing we want to do is we want to write down the conservation of mass principle, which is change in mass within the control volume over time equal to the mass flow rate at the inlet minus the mass flow rate at the exit. In this problem, the mass is not exiting, so this one will be 0. And what we will do is we will take the time and move it to the other side of the equation, and then we're gonna rewrite the equation. Now remember, this is change in mass within control volume. So the final mass minus the initial mass, and that's what we have in here. The mass of the control volume at the final time minus the mass within the control volume at the initial time. Now the mass at the initial time is 0 because we are told from the problem statement that the cylinder is empty, so there is no mass. Equal to, when we move the delta time, we can take the integral from time initial to time final, and then we're going to solve this integral. So we're going to rewrite this in here and solving for this integral. And remember that time initial starts at 0 seconds. All right, so now what we can do is we can solve for the final time, which is what we want to find. So we will take the mass flow rate at the inlet and move it to the other side of the equation. And that's what we have in here. All right, so the mass flow rate at the inlet is given. And what we need to find in order to find the time it takes is the mass within the control volume when it is filled. So how can we do that? So let's take on the side in here. Let's remember something important. Remember that density is what? Is the mass within the control volume at the final time over volume. So density is mass over volume. All right. So here, can we find the volume? Yes. Volume equation for a cylindrical tank is pi r squared times h. So r is half the diameter and h is the length, or how long is the tank. So we can find here the volume and we can find here the volume. Can we find the density? Yes, we can. Remember that density is equal to the reciprocal of specific volume. So how can we find specific volume? A specific volume, you can go to table A-17 at page 919, I think. And you can go to the pressure table for propane. And you can see what is the specific volume at that pressure, and then we can find the density. So once we find the density, we find the volume, we can solve for the mass within the control volume at T final. And once we find this value, we can plug it back in here and we can find the time required. So here we rewrite the mass within the control volume as rho v. Next, we want to find the volume. So the volume, we will simply plug in the given values. The radius is 2 meter and the height, or the length, is 25 meter. So the volume is 100 pi meter cube. Next, we want to find the density. So from the table, which is table A-17 at page 919, now this value, we interpolate this value inside the table, and we got 2 times 10 to the power minus 3. That's the specific volume, which is meter cube per kilogram. And here we were able to find the density. Awesome. So we were able to find the density, volume, and we are given the mass flow rate at the inlet. And remember, we want this to be in seconds, so don't forget the conversion factor. So the time is approximately to fill the tank is 261.8 minutes. Thank you very much. Have a good one.